Hello, Chem 30 students. So we are moving on to chapter 14 here today. Um, so basically we're going to be taking, if you remember in chapter 13, hopefully you remember that, we looked at redox reactions. And so today we're going to start moving forward into chapter 14, which applies everything you learned about redox reactions to kind of a more practical application, which is electrochemical cells. Okay, so we're going to start out by looking at a little bit at the history. So keep in mind with your curricular outcomes, these are stating specifically things that you could be tested on, like for example in a diploma situation. One of the things is to be able to describe science and technology applications that have developed in response to human needs, and to look a little bit at the historical development. Okay, so Alessandro Volta invented the first electric cell. So he did the actual invention, but he got his inspiration from this guy called Luigi Galvani. And Galvani was, he was working on with static electricity, but he was also an anatomy professor. And so, kind of weirdly, he had a dissected frog sitting in the middle of all of his equipment where he was working with static electricity. And some of the different metals that he had around that work ended up, however that might have happened, ended up connecting through this dissected frog. Kind of makes it sound like his lab was a bit of a gong show. But basically, when that happened, he noticed that the legs of the frog started twitching. And he ended up actually doing a lot of work on discovering how important electricity is for like nerves and muscles and things like that. So that's kind of interesting. But basically, Galvani thought that this whole situation was due to some kind of mysterious animal electricity, and it was only Volta who really recognized the experiment's potential. So Volta ended up coming up with an invention that could provide a steady supply of electricity, which wasn't really available at the time. Usually at that point in time, just like Galvani was looking at static electricity, that was the main source of electricity at that time, which was not very dependable. So this electrical cell that Alessandro Volta came up with was really popular because of its advantages over using static electricity. So it produced a steady electric current, which is of course what we want to have if we're trying to power anything. So an electric cell produces very little electricity, right? So originally he just came up with this idea of an electric cell that it was steady and it was good, but it doesn't produce a lot of electricity. So Volta came up with this better design, and you can actually see it in this picture here. We have this stack of like alternating looking kind of substances, right? So basically what he did is he took his original design was how he kind of originally figured this out was that he had these different containers filled with brine, which is just salt water, and between each one he had these different metals connected from each solution to the next. And he found that an electrical current could move through those solutions from cell to cell, kind of, if you consider each one of these a cell. Then he ended up simplifying this and making it a lot more efficient because, imagine how difficult it would be if our batteries were made of like different cups of solution, right? It wouldn't work very well. So instead what he did is he came up with this kind of method where he would have a layer of two metals that sandwiched a thin paper soaked in a salt solution. And that was what he called a cell. Now, in order to make the cell into a battery, you needed to stack all these different cells together. And so this was his revised design. So the more of these cells that you could connect in series, the more power you could get out of your battery, basically. Okay, so a battery is defined as two or more electric cells that are connected in series to produce a steady flow of current. Now there's two types of cells. The first one that we have is called a galvanic or voltaic cell. And so hopefully you can recognize galvanic. Oh, I don't know why I put an A in there. Galvanic or voltaic cell. Okay, and so just recognizing the two names there, right? So if we think about our beginning there, we had Luigi Galvani and Alessandro Volta. So the name is kind of a nod to both of these scientists who helped to, contributed to the information that we needed to build this kind of a cell. So a galvanic or voltaic cell is a cell that converts chemical energy from a redox reaction into electrical energy. So chemical into electrical. And this is basically what batteries are, like the typical battery that we use. It takes chemical energy from whatever ions and stuff are placed inside, and electrodes are inside of the cell. And then because of the connection between the two electrodes, allowing the electrons to flow through whatever is connected in between there, they can produce electricity. Now, the other kind of cell that we're going to look at is called an electrolytic cell. Electrolytic cell. Oops, cell, I guess we need to add that on there. And this is a cell that converts electrical energy into chemical energy, right? So the exact opposite of a galvanic cell, which converted chemical into electrical energy. So basically what happens is you have a power source that is forcing a non-spontaneous redox reaction to occur so that we still have a movement of electrons, but it wouldn't happen spontaneously, so we need to have a power source that's forcing that to happen. So the big thing with an electrolytic cell is that energy input is required. You might wonder, why would we even want to do that? Like, why would we want to force a redox reaction to happen? So we'll look a little bit more in detail at the end of the chapter of why we would need to do that. But first of all, we're going to look at just some of the basics of cells, and then we're going to look at voltaic cells, so that will come a little bit later. So electric cell structure in general, so this applies to both types of cells. All electric cells are composed of electrodes. Sorry, two electrodes, I guess is what I should say there. Two electrodes. And so those are solid electrical conductors and at least one electrolyte. So just think back to just remembering some of your vocab there. We looked a little bit at electrolytes in redox reactions. So remember that these are aqueous electrical conductors. So this is going to be ions basically that allow a charge to move in solution. Okay, so two important components here, the solid electrodes and the aqueous ions. So here you can see in a general, like this happens to be an electrolytic cell, but for either electrolytic or voltaic, they're both going to have these solid electrodes, two of them, a positive and a negative, and they're also going to have some form of an electrolyte. So at least one electrolyte, usually more. In voltaic cells, so in like a traditional battery, the electrolyte is often just a moist paste, so it's not like a full kind of solution the way we often think of it. There's just enough water added in it so that the ions can move. Okay, so that's why when you if you shake a battery, you're not going to hear water sloshing back and forth in it. They just make a moist paste in there. So in this one here, we have copper and chloride ions that are our electrolytes, and then we have electrodes, and they don't actually specify in this image what the electrodes are made out of, but they're going to be made out of some kind of solid metal. Okay. So we're going to look at classifying electrodes in a couple of different ways. The first one is that an electrode can be considered inert or active. So an electrode is a solid electrical conductor. So remember, that just means a conductor is always referring to something through which electrons can easily flow. So this is usually going to be a metal or carbon rod. Those are going to be our two main options in a cell where the electrical connections are made. Inert electrodes are inert, always means chemically unreactive. Okay, so when we're looking at unreactive, usually the electrodes are going to be made out of platinum or carbon. Those are our two usual choices for that. So we use inert electrodes when the reduction or oxidation half reactions that we're using do not require a solid. Okay. However, if a solid is required for one or both of those reactions, then you would use an active electrode where it's actually going to participate in the electrolysis. Okay, or in the, I guess electrolysis might be a little bit misleading because it sounds like it's just for electrolytic cells, but just remember that they're going to be participating in the redox reaction, the overall redox reaction. So there's two types of electrodes. The first one we're going to look at is called an anode. So just keep in mind when you're like thinking about vocabulary for this, electrode is the general term, so it can apply to either of the two types, and then we're going to look at the specific names, which are anode and cathode. Okay, so the anodes and cathodes are the types of electrodes. So in an anode, anodes are where the oxidation of the strongest reducing agent takes place. Okay, so keep in mind with oxidation, what does that mean is happening? It means that electrons are being lost. Okay, so we represent what's happening at the anode by an oxidation half reaction. And depending on the type of cell, we either label the anode as being negative or positive. Now, there might be differing, like there's not a lot of information in your textbook about this, and there might be differing opinions as to why these different signs are assigned to these different, like to anodes in the different cells. But basically my best understanding of this is that in a voltaic or galvanic cell, because we have a spontaneous reaction happening, let me just see here. Let's look at a voltaic cell here really quickly. So at the anode, we have spontaneous oxidation, right? Because this redox reaction is going to be spontaneous, so much so that it can provide power to an outside source. So the anode, where oxidation is happening, that means electrons are being lost here and then transferring over to the cathode, which has that positive charge, right? So the electrons are wanting to flow from an area of high concentration to low concentration. So in order for that to happen, we get this initial kind of accumulation of electrons as the oxidation is occurring and they start to flow out. And so we label in a voltaic cell, we label it negative because of that oxidation that's happening with the initial accumulation of those electrons as they're lost through the reaction. Now with electrolytic cells, it's a little bit of a different situation. Remember that we're still going to have oxidation happening at the anode, but this is not a spontaneous reaction, right? So the reaction, the reduction half reaction that's happening at the cathode is not spontaneously going to be able to attract the electrons from the anode. And so we need a power supply to basically make that happen, force the electrons to move from the anode to the cathode. So we still have this oxidation reaction happening here, but there isn't enough of a difference here with the reduction half reaction happening at the cathode to pull those electrons. So the power supply, we attach the positive terminal of it so that the electrons still want to flow from that area of higher concentration, they're being produced through the oxidation, to this area of lower concentration, which is the positive terminal of our power supply. And so because our positive side of the power supply is attached here, we call the anode positive in an electrolytic cell. Okay. Now there is memory devices for both of these different types of cells. Personally, I like to just kind of know the logic behind it so that if I forget, because we'll kind of look at multiple mnemonic devices throughout this unit. So if you ever feel like you might get too overwhelmed with those, as long as you know the logic of why one would be positive versus negative, you can always come back and reason your way through that in a test, which, as you guys probably know by now, is the best way that I like you guys to think about things, is just with logic. So the other type of electrode we have is a cathode. And as you can probably guess, this is where the reduction of the strongest oxidizing agent takes place. So reduction half reaction is represented in the cathode side of the cell. So obviously we're going to assign opposite signs to our electrodes for this electrode. Sorry guys, totally just spaced out there for a second. So in a voltaic or galvanic cell, that means we're going to say that it's positive. And that's because we have reduction happening at our cathode, which means for reduction to happen, electrons are being used up, right? So we have this deficit in electrons as they're being used to fuel this reduction half reaction, which is why electrons are going to continue to spontaneously flow from the anode. Okay, so that's why that's called positive. Negative in an electrolytic cell, same reason as before, we have this non-spontaneous reaction. So in order to force electrons basically to be accepted for this reduction half reaction, our negative end of our power supply is attached on this side, and the repulsion is going to force the electrons to the cathode, where the reduction is going to happen. And so this negative charge from the power supply is why we label the cathode as being negative. Okay, just keep in mind, like, the main important thing is that you know that they're labeled negative and positive, not so much why, because there's slightly, as far as I could understand, there's slightly different reasons for why we label them negative and positive. You know, with an electrolytic cell, it's because of the positioning of the power supply, whereas with a voltaic, it just has to do with the reduction and oxidation reactions. You shouldn't be asked any questions on why that would be, but you definitely do need to know that one is negative and one is positive, and which one is for each one of these types of cells. Okay, so again, we have a memory device, usually with a voltaic cell. When we have it set up in a diagram, the anode will always be on the left and the cathode will always be on the right. And because oxidation happens at the anode and reduction happens at the cathode, you can kind of just remember that both of these will be in alphabetical order if you're reading left to right, which we do in English, right? So it goes anode and then cathode. So A comes before C in the alphabet, and also oxidation, like O, comes before R in the alphabet. Okay, so both of them are in alphabetical order from left to right. Now, of course, the only version of this picture I could find is going the wrong direction, which isn't great. So the main thing that I would pull away from this is, for me personally, this is the most mnemonic device that stuck with me really well, is that we have an ox and a red cat. So just always remembering that anode goes with oxidation and reduction goes with cathode, okay? And so even if this is not in the right positioning, if you can just always remember anox and red cat, then for me personally, that's the one that kind of has helped me the most when I've worked through these units. Okay, so we're going to look a little bit at some terminology for these cells. So thinking about electrodes and electricity, first of all, what is electricity? Well, electricity is just the flow of electrons. So electrons move from the negative anode of a battery through any object that they're producing electricity for and to the positive cathode, right? So essentially what we see here in this particular battery, the zinc casing is the negative terminal or the anode. And so it's producing electrons that when it's hooked up to this wire, right, they're going to start flowing through there as long as there's a place for them to go to, which means this wire has to complete the circuit by ending in the positive terminal. So if we didn't have this bulb in here, if we just had the wire, the electrons would just be moving from negative to positive. If we connect this bulb so the electrons can flow through the wire, through the bulb, and then, you know, into the wire on the other side and back into the positive terminal, the electrons that are moving through this device, whether it's a light bulb or a speaker or whatever it might be, are going to convert that flow of electrons, the electrical energy, into whatever it is that you want, right? Whether it's light energy, sound energy, whatever that might be. Okay. Really quickly, here is a practical application. So if you think about how electrons are flowing, you can use information about cathodes and anodes when in application with batteries. One of the most ways, to me, like lots of people aren't might not always test the voltage of a battery because, like, for example, in a car, we kind of like, as long as it's running, we just assume it's running. But you can use this to test the voltage of a battery. I'm going to jump through this really quickly because this isn't something you'll be tested on, but it is always nice to think about how what we're learning can be used in real life. To me, one of the more practical things is knowing how to boost like a dead battery. So always remember first red, right? The R goes with first, and last is black, okay? So the L making that together there. Now this one is actually not drawn perfectly because actually what you usually want to do is your first step would be always connect the red, the positive, to the live battery, the boost battery, and then the other red end to the dead battery. Then, because if you complete the circuit, right, so then the third thing you would do is connect the negative here to the live battery. Now, what we don't want to have happen, what would happen if we hooked up the red last? Well, we would already have this negative terminal connected, which is where the electrons are going to be coming from. So then if we had this already connected, which is like hooking up to the source of electrons, then if you attach this positive one connecting the circuit here, if this last red one hits anything other than like the battery, you can end up producing sparks, right? Because you're going to have a flow, like a current, that can end up being dangerous. So that's why you always want to connect the red first, right? Because it's just the positive where the electrons can flow into, then connect the negative. And then you always want to reverse the order when you're taking them off. So one last thing to also be aware of is you connect the final black, I don't know what you call that, the clip-on thing. You connect it to somewhere on the engine block. So you find like a bolt or a screw or something like that that you can connect it onto, not onto the dead battery. And then to take it off, you first take off the black lead from the dead battery, and then off of the good battery, and then your red off of the dead battery, and then your red off of the good battery last. Okay, so in reverse. So just a little practical application because we all know how much students like to ask, why do we need to know any of this? Okay, so electrical potential difference is the next term we're going to look at. So we thought a little bit about electricity, the movement of electrons. Electric potential difference is something that we can measure with a voltmeter. Okay, so a voltmeter is a device that measures voltage, which is another word for electric potential difference. So make sure that you know that these two words are interchangeable. So electric potential difference, maybe I won't really write it out here. Electric, but you can fill it in. Potential difference, which is voltage, is the difference in charge between any 2 points on an electric circuit, right? So that's why when we have these, like a good electric circuit that has a good current flowing, we have a negative and a positive terminal, right? There's a difference in the charges. And so that is what's going to allow the current to flow. All right. Sorry, guys, the recording from home now makes things a little bit different because if the mailman comes by, my dog starts to lose his mind. So I just wanted to pause really quickly there so you didn't have to listen to him barking. Okay, so yeah, we have the difference in charges, right, which is the voltage, and that's causing the current to flow. And basically, the greater the difference between these two, the quicker, kind of like, it's hard to say it, but like the more power there will be behind the movement of the electrons. So that means the more power there is behind the movement of electrons, the more power we're going to see in whatever it is that we're trying to power. Okay, so this here, we call this E naught. So this little degree sign we call naught. So this is the symbol that we use to represent electric potential difference. And this is helping us to understand that that's happening at SATP, so at standard atmospheric or standard ambient temperature and pressure. Sorry, I always want to say atmospheric there, but okay, so in an electrical cell, Oh, and actually maybe I'll just point out really quickly. So remember from our reduction half reaction table, you can actually see that we have, for different reactions, we have the electrical potential, right, with that little symbol there. And then the units that we use to measure it are volts. So here we can see a comparison for all these reactions of what the electric potential would be. And so if you think about what we learned in chapter 13, which is that, like for example, for a reaction to happen spontaneously, we need to have a reduction half reaction that's higher in the chart than our oxidation half reaction. And look at what's happening with the numbers, right? Positive 2.87, 1.5, 1.2, 0.84. So we see that the numbers are decreasing down to 0 here with the hydrogen, and then going into the negatives. And so when we have this difference between them, you can understand why those reactions would be spontaneous, because we just said you have a difference in charges, right? That's basically allowing the reaction to proceed. And we know that's true because there has to be a difference in the position on the chart for the reaction to be spontaneous, which represents a difference because we have decreasing values for our voltage represents a difference in our electrical potential. And so that's where we see that spontaneity coming in. So in an electrical cell, there is a difference in charge, which is how many electrons we have between the two metals, right? And that's why we have negative or positive charges at the different electrodes. The greater the difference, the more, there's not really a good way to say this, but because it's not actually pressure, but the more quote unquote pressure there is for electrons to move, right? So a change in the voltage basically is going to create more pressure for the electrons to move. So if you connect the two metals that have the different charges, right, you have negative and positive, then the electrons want to move from an area of high concentration to low concentration. And when the electrons are moving between those areas of concentration, that's called a current. Okay, so it's just really important that you guys have these two pieces of terminology separate. Voltage is looking at the difference between the charges, whereas current is the actual movement of electrons because of the difference in the charges. So you can kind of think of it using this analogy of water flow. Water pressure represents the voltage, right? So if you think about a waterfall, what's causing this water to flow over? Well, I mean, it's potential difference because of like it has potential energy. If you remember back to when would have been the last time you looked at that, probably Science 10, potential difference, right? So, and we know that that changes into like potential energy here because of its location, changes into kinetic energy as it moves down, right, to an area of lower potential energy. So we see that transformation of energy, keeping in mind conservation of energy is applicable there. So the total amount of energy isn't changing, but how it's like applied is changing. So water pressure represents voltage. So it's causing the flow from high concentration to low concentration, right? The pressure there. So if we apply that to an electrical cell, if you think about an anode has a lot of electrons because of the oxidation that's happening, so it has a negative charge, and then the cathode has reduction happening, so it's using up electrons, so there's less electrons, lower concentration, so it has that positive charge, and the difference between those is what's going to make the current happen. Okay, so the volume kind of represents the charge. The more water there is at the top, the more pressure it's going to fall with, right? Versus like if there's just like a little trickle of water. So essentially the volume is representing how much charge there is. So if you have like -1 and +1, there's going to be a less difference in charge than if you had, say, -3 and +2, for example, right? There's more of a charge. So the difference, which is the voltage, is going to be increased. If the amount of water at the top decreases, like we just mentioned here, if it's just like a trickle, then we don't see as much pressure happening in the waterfall, right? Same thing with an electrical cell is if you have less of a difference in the charges, the voltage is going to be decreased. The voltage is like the pressure with which it's moving, okay? Another thing to kind of keep in mind here is how those differences in voltage apply practically. So if you have a 9-volt battery versus a 1.5-volt battery, there's 6 times more of a difference in the charges in the 9-volt battery than there is in a 1.5-volt battery. And as a result, the 9-volt battery can actually release 6 times as much energy as the 1.5-volt battery. Okay, so the voltage of a cell, what determines that? What determines how much pressure there's going to be for movement? Well, it depends mainly on the chemical composition of the reactants, because depending on what their charges are, right, the differences are going to affect the ability or the movement of the current. And so it's not the physical size of the battery that matters as much as the chemical composition of the reactants, right? Because the difference in their charges is what's going to affect movement or voltage. Okay, another little piece of vocab here. An ammeter is a device that measures the rate of flow of charge. Okay, so keep in mind we talked about a voltmeter, which measures the electrical potential difference. So that's looking at the difference between those charges. Whereas with an ammeter, we're measuring how fast the electrons are moving past a certain point. And so this is actually measuring the electrical current. Electrical current. Okay, so just keep in mind, voltmeter is measuring like how much pressure there is for the current to flow, and ammeter is measuring how fast basically these electrons are moving past a certain point. The larger the electric cell, if you have the same chemical composition, the greater the current can be produced. Okay, so just keep in mind when it comes to voltage, it's going to depend mainly on the reactants. But then if we want to increase the amount of current that can go for one specific like set of reactants, right? The larger the cell is, basically the more stuff that you have in it, the greater the current can be produced, okay? And so that's why we do see like a car battery is larger, right? So there is differences in the size of batteries and how much power they can generate. So some kind of like, what do you call it? Analogies again here. Electric potential difference, so that's our voltage, is like the potential energy difference between 1 kilogram of water at the top of the dam and 1 kilogram at the bottom of the dam. So remember, potential energy is if you have a kilogram sitting up here versus here, if this was opened up, this would have a lot more potential energy, right? Because it's going to start flowing down the second that's open. Whereas with this, there's not really that downhill trajectory for it to move into like an area of lower concentration. So like if this was a lake and not a river where it, potentially probably would have continually lower and lower elevations. But if this was just a flat area here, the water is going to come rushing from this area, and then once it comes to this part, it's just going to slow down, right? So electric potential difference is looking at the difference between these two areas, whereas electric current is just looking at the actual flow of water, right? So if you wanted to have more electric current, more flow of water, what would you need to do? The voltage is going to be affected by the difference in position, but the current can only be increased, so you can only have more water flowing through here if you widen this space, right? So the more water that's flowing through, the greater the current would be if you were measuring like how many water molecules, for example, were moving through here. Okay, so more water can flow if you have a greater space, and that's true for electric cells as well. The more material you have, the more current can be produced. Okay, let's look at some electrical quantities. So the first one we're going to look at is power. And power is the rate at which electrical energy is produced. Okay, so it's how fast is this happening? We measure it in watts, and it's calculated using the formula power is equal to I, which is the current, multiplied by V, which is the voltage. So if you think about how fast do we have electrical energy being produced, if we think back to the picture we just looked at, the most, like in this dam example, the most water movement that's going to be happening is if you have a big difference between the two areas, so that the water wants to move really fast, right? We know that water will move faster down a steep slope than a gradual slope. So if we have a big difference between those two, which in electrical terms is voltage, and then if you have a lot of space for the water to flow through, that's also going to mean that we have more movement. So together, these two things increase our amount of movement that's happening, whether we're talking about water or electrical current, right? And so power has to account for both of those factors in order to represent how much electrical energy is being produced. Okay, the other thing we have here is energy density. And so this is measuring how much energy is stored or supplied per unit of mass, right? So if we have, these reactants and stuff making a redox reaction, we want to know how much energy is produced per unit of mass for that reaction. And so this is measured in joules per kilogram, right? So you have a table here that talks about the substance electrical quantity we're talking about, what symbol we use to represent it, how we measure it, the units we use for it, and the symbol of the unit. You do also have in your data booklet, if you go to page 2, you'll find that a lot of this stuff is mentioned in here. So make sure, like I always say, make sure you know what's in your data booklet before you write a test, so you know what's available to you. So for example, charge is here. We represent it as a variable with the capital letter Q, and the units that we use to measure it are capital C, which is coulombs. Okay. Current, represented with a capital I up here. So this is the variable that stands for current. The units we use to measure it are amps or coulombs per second, right? So coulomb is a unit of charge. How many are going by per second? And amps is just like a simplified version of that. The nice thing about this unit is that it actually kind of helps us to remember what current is. It's the movement of charge over time. Potential difference, measured in volts, is up here. So it's a little bit, remember, standard electrical potential is the same thing as potential difference. The symbol we use for it is this capital E with the degree sign. The units we use for it are volts, or you could have joules per coulomb. Okay. Let's see. Power, represented with a capital P. I think this is the only one we actually don't have on here, because here we have pressure. We don't actually use power a whole lot until later on in this chapter though, but so you might just have to know this one, which is why I recommend that you look at this ahead of time so you know what's available to you, right? So power is measured in watts or in joules per second. So again, this is helping us to remember what power is measuring. It's the electrical energy that's produced per unit of time. Okay, and then last of all, we have energy density, which I also believe is not measured. It's not in your data booklet, so you'll just have to know energy density is joules per kilogram. Okay. All right, let's talk a little bit about types of batteries. So mainly when we're looking at types of batteries, we're thinking about how they are fueled, essentially. So remember, batteries are one or more electrochemical cells, right? Remember when we looked first at Volta's design there, you have multiple cells that are connected. with the ability to produce voltage. So the first kind we're going to look at is primary cells. So this is the standard kind of battery that you probably think of, that you can recognize here. It's non-rechargeable. So basically you have chemical reactions happening in there, redox reactions, that are not reversible. So basically once you have the chemical reaction is complete, the battery can no longer produce voltage, and they're disposed of, right? Now, the advantage to them is that they're relatively inexpensive. So they have a set amount of material in them. The reaction runs as long as you're using the battery, and it'll run up to a certain point until it can no longer fuel the redox reaction. And then at that point, you basically have a dead battery and you just have to discard of it. Okay. Some information there about capacity fade, which we're all familiar with, so you can always read that yourself. Secondary cells are rechargeable batteries. So basically what happens, same kind of an idea as the primary cell, where you have a redox reaction happening to create the power, but essentially what happens is you can reverse that redox reaction by plugging it in, right? So when you recharge it, you plug it in, you supply electrical energy to reverse the reaction because it's non-spontaneous, and then it's ready to go all over again when you start to use the battery again, right? So products can form reactants and vice versa. So this is nice that they can be recharged because it's less waste of materials, but they definitely cost more. Okay. So discharging a cell or battery is like letting the water spontaneously run out from a higher level behind a dam, like we talked about with our analogies there. And then charging is basically like pumping the water back up behind the dam, right? So it's non-spontaneous. You have to put in work to get it back there. This was kind of interesting too. Chinese scientists successfully created the world's first rechargeable sodium carbon dioxide battery. Now it's carrying more energy per weight than lithium ion batteries, which is obviously useful for space travel because they want to minimize weight, but it's also good because there's the atmosphere of Mars is carbon dioxide rich, so that can help when we're doing exploration there. Last of all, we're going to look at fuel cells. This is the one that you're probably not familiar with out of the three types. So this is where at least one of the reactants is continuously being supplied to keep the cell operating. Technically, a cell like this could continue working forever as long as reactants are supplied. So basically what happens here is you have oxygen and hydrogen that can be continually supplied, continuously pumped in, and then they react, with the reduction and oxidation half reactions to produce power. So this is really efficient. It's used for, again, with space exploration, and it actually produces clean water. So, I mean, what more could we ask for? The only big problem with it is that it's too expensive for general or commercial applications. So unfortunately, we can't have that commonly accessible yet. Here you can see a difference in the efficiencies of different technologies. So remember, efficiency is just like for how much power is being put in, how much useful power is put out. And with fuel cells, that's 40 to 70% compared to like a car engine is 17 to 23%. So a huge difference, right? Okay, so really quickly, let's do an overview of what happens in an electrochemical cell, and then we'll be finished for today. So a general overview of both voltaic and electrolytic cells. So this will apply to both types of cells. Okay, so let's start at the anode, which is where oxidation happens regardless of what type of cell we're looking at. So oxidation means electrons are being lost, right? Those electrons are going to flow towards the cathode. In a voltaic cell, that's happening spontaneously. In an electrolytic cell, it's being powered by a power supply here. Okay, so electrons flow towards the cathode, and then at the cathode we have reduction of the strongest oxidizing agent. So that means the electrons that are coming in are being used to fuel this reduction half reaction. So electrons are being consumed. And then, what else do we have here? So the anode is losing electrons through the oxidation of the strongest reducing agent, which means it's becoming positively charged, right? And with this positive charge, what's going to happen is anions, because we know that both of these electrodes are in solutions. We mentioned how it was important to have an electrolyte for any kind of electrical cell. And so anions from these solutions are going to be attracted to this positively charged electrode. Okay, so this is basically going to happen where these negative sulfate ions are attracted over here because of the positive charge, so that we don't end up with a big charge difference in these solutions. So the negative ions are going to travel here to balance out the charge. So they travel through this thing called a salt bridge, which we'll talk about more at a later time to understand that. But basically it just connects these two half cells so that we can have a movement of ions or electrolytes. Okay, so if we look at a specific example of this where the anode is being oxidized, in this particular one we have zinc, which is at our anode, and essentially what's going to be happening, oh right, sorry guys, I forgot to change this on my printed paper. I changed this on the one that you guys have, so hopefully this will be fixed for you guys. So it wasn't copper at the anode, it is zinc. So zinc metal in this case converts to an ionic compound, right? So we have zinc here, and then as you can see in this reaction here, because of the oxidation that's happening, we have zinc 2 plus ions being formed. Okay, so it gains a positive 2 charge. And what we end up seeing in a practical sense, if you look at this actual picture of what would happen in this situation, our zinc anode, you know, before it looked like this, and you can see what's happened to it. It's been eaten away, right? And that's because this solid zinc metal, like you can see here, is forming these zinc 2 plus ions, okay, through that oxidation reaction. And then what you can notice is if you compare the two of these, there's an equivalent. As much as this one got whittled down, you see that this one looks like it's growing, right? And so that's at the cathode. We actually see an accumulation of solid metal, okay? And I believe I have that in the next one. So at the cathode here, we have reduction happening, right? Which means that the electrode is becoming negatively charged. Now, in terms of electrolyte movement, this is going to attract zinc ions from here, which are positively charged, into this half cell where we have the negatively charged electrode, right? Through the attraction of opposite charges. So zinc 2 plus ions travel through the salt bridge into this half cell because of the attraction to that positively charged cathode. And then, so here we can see what's happening. The copper 2 plus ions that are in solution are being reduced to solid copper metal, which means they're building up on that electrode. And so we see this accumulation of solid metal on there. Okay. All right, so that's pretty much everything. There's a little bit of a summary here of the components of an electric cell. Make sure you're familiar with all of these, that you have to have 2 electrodes and an electrolyte. The electrode is a solid conductor. The electrolyte is an aqueous conductor. Cathode is positive depending on the cell, so that's not maybe the best thing to remember. Anode is negative. And the electrons flow through the external circuit from the anode to the cathode, and that happens regardless of what type of cell we're looking at. There's also some information here you guys can look at developing advanced lithium-ion batteries. As you know, we're constantly trying to get better batteries so that we always have access to our phones. Last of all, you guys have some practice problems you can try here before you move on to the next section, which is where we're going to be looking at voltaic cells. So I will see you then.